All right, we're going to do a little more complex stoichiometry problem now. We're going to convert from grams of something in a chemical equation to grams of something else. And this would be a more real-life type situation if you're working in a lab, because we can easily measure grams of something. We have a balance. We can weigh how much of one thing we're adding to one thing another. So let's look at this stoichiometry problem here. So in the stoichiometry problem, again, we're going to convert from grams of one substance in a balanced chemical equation to grams of something else. And remember, these stoichiometric coefficients give you the relationship of moles of everything within the equation, and they allow us to go from one mole map to another. So if we start with grams of something, and let's say that this is our mole map of oxygen down here, and this is our mole map of propane up here. This question is saying we're starting with 702 grams of propane, of octane, not propane. And so if we have grams of octane, we can go to moles of octane. And again, those stoichiometric coefficients allow us to go from one mole map to the other. So if we have moles of octane, we can go to moles of oxygen. Then once we have moles of oxygen, we can go to grams of oxygen. So again, if we're drawing our kind of roadmap, we're going to say that we're starting with grams of octane. And once we have grams of octane, then we can go to mole of octane. And once we have moles of anything in the equation, we can go to moles of anything else. So then we can go over to our moles of oxygen using our stoichiometry. Once we have moles of oxygen, we can go to mass of oxygen or gram of oxygen. Right, and so this is kind of the roadmap of how we're going to solve this problem. So you can see we're going to need 1, 2, 3 conversion factors here, right? And so if we're starting our problem with 702 grams of octane, and the next thing we want to do is go to moles of octane here. So what we need to know is the relationship between grams of octane and moles, and so we need to know our grams of octane on the bottom. And again, the relationship is based on the molar mass of the compounds that make up that molecule. So remember, we have 8 carbon atoms, and each of those weighs about 12 grams per mole. And if we look at hydrogen, we have 18 of those, and each of those is about 1. So we have about 96 grams per mole plus 18 grams per mole. So our molar mass is somewhere around 114. I think the more accurate number would be 114.23. So 1 mole of octane will weigh 114.23 grams. Now the next step we want to do is go to moles of O2, and we want to get rid of what's on top. We want to get rid of our moles of octane, right? And so to do that, then we need our stoichiometric coefficients. Remember, this balanced equation tells us if we start with 2 moles of octane, we're going to have to react that with 25 moles of oxygen. We're going to produce 16 moles of CO2 and 18 moles of water. All right, so our relationship here is 2 to 25. So we need 25 moles of O2 for every 2 moles of octane. Right, so now we've gone from grams of propane to moles of propane, now to moles of oxygen. Now we can go to grams of oxygen. So we need to know the relationship between grams of O2 to moles of O2. And again, we're going to get that factor from the periodic table, right? We have 2 oxygens, each their mass is 16 grams per mole. So we'd have 32.00 grams of oxygen. For every mole of oxygen, our grams of propane cancel, our moles of propane cancel, our moles of O2 cancel, and we're left with grams of O2. So if we plug that in our calculators, we're going to multiply everything on top and divide it by everything on the bottom. You should get something like 2.46 times 10 to the third grams of O2.